In this video, I will talk about analog to digital converter, ADC. The ADC, analog to digital converter, convert the analog signal in terms of voltage, as you see here on the figure, to a binary form or digital form, zeros and ones. This happens using a sampling technique. The ADC samples periodically the input signal in terms of voltage, as you see here in this figure, to obtain like an approximation of the discrete values of the signal. So here, the sampling process happened on a certain frequency, and it's like dividing the signal, as you see here on the figure, into discrete parts. This represents a discrete vector. As you see here, it divides or samples the analog signal into levels like this, and these levels are mapped after that to the digital equivalent of it. Here you see different shots from the sampling of the analog signal. Here, if you have a slow frequency, so the sampling process happened on a wide range, as you see here on the signal. And as we go to up, the frequency is increasing, or the conversion rate from the analog to digital form is increasing. Then after sampling and making like a screenshot from our signal with these discrete values, this is the squares that you see like this, the analog signal is mapped to the digital form. For example, if we see that this voltage value is equivalent to 0, 0, 0. This value of voltage is mapped to 0, 1, 1, and so on until here. This is the maximum value of the signal, which is mapped to 1, 1, 1. So the lowest value of the voltage, it's mapped to 0, 0, 0, and the greatest value or the maximum value is mapped to 1, 1, 1. The number of bits here is defined on the ADC. You will see on the ADC the number of bits of the ADC. So if we take this example, the number of bits of our ADC will be a 3-bit, okay? And this process is called quantization. The minimum difference between two analog voltage value is called the resolution. The resolution is calculated based on the n bit of the ADC that we talked about from a while. For example, if we have a 10-bit ADC, so like our ADC on the 8MeGA32, we are expecting that the analog signal will vary from 0 volt to 5 volt. So this levels of voltages, the ranges between the 0 volt and the 5 volt, 0 volt represent the VRF negative, which is the minimum value of voltage that our ADC operating on, and the 5 volt represent the V reference positive of our ADC, which is the maximum value the ADC operating on. So the resolution is the maximum difference or the, sorry, not maximum, it's the minimum difference between two analog voltage values on the range of minimum 0 volt to 5 volt. So how we calculate the resolution? The equation is here. The resolution equal the voltage range over the number of steps. The voltage range, we said that we have 5 volt, which is the V ref positive, which is the maximum voltage, and we have the 0 volt, which is the minimum voltage. Then we divide it by the number of steps. The number of steps is calculated using the bits of the ADC. So if we have, for example, 10 bit ADC, so 2 to the power 10, it will be the number of steps that the ADC is having, which is 1024. And by calculating this equation, we will have a resolution of 0.0048. So if we look in this figure, we will see that the minimum difference between the 0 volt and the next level of voltage is 0.0048. We have two main ADC types. The common ones is the flash ADC and the SOR ADC. Flash ADCs, flash يعني means direct conversion of the analog signal, and the other one is successive approximation. The one inside the 8mega32 is the successive approximation ADC. So let us see the architecture of each one, and then we will have a comparison between the flash ADC and the successive ADC. The flash ADC it's the fastest way to convert from the analog signal to digital form. This happens because if we see here the architecture, we have like a group of comparators. This group of comparators are connected to the ref negative and the ref positive value. If we focus here on this comparator, you will see that the positive side is connected to the analog input coming to the ADC, while the other one is connected to the to this voltage value. This voltage value is determined based on the voltage difference between the VREF negative and the REF positive. Here in this range, it will be like a small voltage value because we have only a one resistance between the VREF negative and VREF positive, and the voltage as you go from here, from the VREF negative to the REF positive, the value of the Vx voltage is increasing. This comparators number determined by the n bit of our ADC. So if we have an ADC of 10 bits, so we'll have 10 comparators. As you see here, also it's determined by a simple equation, which is called 2 to power n minus 1. So it will give us 2 to power n minus 1. It will give us the the range of our ADC, which after that it will be mapped to the number of bits that we have by this encoder to determine the least significant bit and the most significant bit of our digital form or the converted analog signal digital equivalent. So here, in each comparator, it happens like a comparison between the voltage value here, which is here Vx1, and the value coming from the analog input. So if the value of the reference is less than or less than of the analog input, so here it will gives a 1. But if the value of the reference voltage is greater than the input voltage, it will give a 1. So here, as we go, that means that on a summary, that if the input voltage here is greater than this comparator, that this voltage level, so it will be a 1, and that means that it's greater than this range. All comparator works simultaneously in the same time. So the result goes to the output of the ADC at once on the same time and is converted. So this is the reason that this ADC have a high speed. Also, I want to confirm about the levels that as we go up on this ladder of resistances, if the input voltage is greater than the reference voltage connected to the comparator, it will gives a 1. But if not, it will give a 0. So this is how the flash ADC is working. Let us see the SAR ADC, or the successive approximation ADC. This ADC is depending on the binary search algorithm, and most of ADCs is working from for like a sampling rate of 5 mega sample per second. This SAR ADCs also ranges from 8 to 16 bits. As you see here on the diagram, that we have only a one comparator compared between comparing to the flash ADC. We have here like a group of comparators based on the number of bits of the ADC, but here we have only a one comparator. This comparator make the process of comparing the values of the reference voltage and the input voltage bit by bit. It's not making the comparison simultaneously in the same time. So this is the reason that the SAR ADC is slower than the flash ADC. So let us analyze the architecture in details. So in this block, the track and hold is like a filtering or zooming for the signal coming, the analog signal to the comparator. Here is a DAC. DAC means digital to analog converter. So this DAC responsible for determining the value of the reference that we are comparing our reference voltage to the reference voltage of the bed that we are working on now, or the comparator. So the analog input voltage is held on the track hold, and the reference value or the maximum analog amplitude expected is given to the digital to analog converter block here. And the number of bits of the DAC should be the same number of bits of the ADC that working. And this VRAF, it can be, for example, as we see before, it can be the 5 volt, which is the maximum value that the ADC is operating on. Then this block, it generates 2 to the power n analog voltage value from the reference value provided here. And this done by dividing the reference voltage by 2 to the power n steps. Then this voltage is representing this VDAC is connected to the negative plug of the comparator, and here the input voltage coming from the track and hold module to the comparator. At the beginning, the input voltage is compared with V reference over 2, and if the input voltage is higher than the Vref over 2, which is the value of the VDAC in this part, the comparator output here a logic 1, and the bit n by 2 is set to a 1, and here the n bit register, it will be n by 2 set to a 1, which is given as the input of the block, the SAR logic block here. As you see here, this is the SAR logic. This SAR logic decide which will happen in the next iteration. This what I explained, this is at the beginning of operating of the ADC. Then at an input of 1 at bit n over 2, the SAR logic block here will input the voltage value, يعني will determine or recognize that the input voltage value here lies in the upper half of the original voltage range, which is from Vref2 and Vref, and the new iteration. So for this sake, the new iteration begins with the input value being compared to 3 Vref over 2. The 3 Vref over 2, this is the midpoint of the range from the Vref over 2 to Vref. Okay, so this value goes here to the DAC, and the VDAC here, يعني this happened to narrow the range of our voltage, to localize the exact value, or the يعني semi approximated value of our voltage. So the value we are comparing the V input, our V in with, which is the VDAC, will be changing to be Vref over 2, and this is the minimum voltage of our range, and Vref is the same, the maximum voltage. So if so VDAC, it will be equal VREF over 2. If the Vn is lower than VREF over 2, so the comparator logic here will output a 0. Here will output a 0 to the SOR logic, and then the SOR logic will decide what will happen on the next iteration, which will determine that the VREF, we have to make our range narrower than that, and so on and so on. We narrowing the range of the value of the voltage until we determine the exact value or the nearest approximated value of our voltage. This is how the SOR ADC is working. So after exploring the two architectures, we want to make like a quick comparison between the two ADCs. Here, if we make the point of comparison, it's the conversion method. So the flash ADC is working by a parallel array of comparators. As we see, we have like an array of comparators, and every or each comparator is connected to the input voltage and the reference voltage related on the array of resistances, and also the conversion from analog input to digital input. It happens directly, simultaneously on the same time. But on the other hand, the SOR ADC, it uses the binary search algorithm, and it produces an approximate approximate mapping of the input voltage to the digital output. As we see, we have only a one comparator, and it's working by the binary search algorithm, and it's taking time to determine the equivalent digital output. For the speed, here the flash ADC is faster than the SOR. As we say, it's a parallel processing nature. We are the comparators are working simultaneously in the same time, and at once they produces the digital equivalent of the analog signal. But here the SOR is working by iteration, so you need a multiple clock cycles to complete the conversion process from analog to digital form. For the resolution, the ADC have a limited resolution because it needs large number of comparators, and these comparators have to be efficient and reliable. But here, the SOR ADC, you can make a high resolution by fewer components, because we have only a one comparator, one DAC, and some registers. So it's not the resolution is very high. Other point of comparison is the complexity and power consumption. The flash ADC have a more complex design, as we see on the architecture, and due to the large number of components, we also have a high power consumption. Compared to the SOR ADC, it's less complex architecture, and it will result on a less power consumption. For the accuracy, the flash ADC have low accuracy, because it may have from a comparator to a comparator, we may have a mismatch on this comparator, and this is a famous problem on the electronics world and the comparators. The mismatching and also the propagation delay. Maybe one of the comparators have noise, have a delay, have any issues from the electronic problems. So it has a less resolution compared to the SAR that it has a high accuracy compared to the flash. For the applications, the flash ADC, because it's fast, so it will be a perfect match for the high-speed conversion applications like digital oscilloscopes, radar systems, and high-speed data acquisition. The SAR, it will be more fit for the applications that needs a high accuracy, power efficiency, and moderate speed, like sensors, medical devices, and consumer electronics. Now, we can also highlight the frequencies that we are working on. We know that the 8MeGa32 is working on a range of 1 megahertz to 16 megahertz. But here, the operating frequency for the ADC, it's like 3486 hertz to 77 kilohertz at maximum. So we will need to make prescaling for our frequency, so it can fit for the frequency required for the ADC sampling process. Now let us see the registers needed for the ADC. We have 4 main registers. The first one is the ADC multiplexer selection register, then ADC control and status register, ADC data register, and special function IO register. For the ADC multiplexer selection register, which is called ADMUX, the ADMUX is responsible for 2 functions. The first one is that we determine the ADC channel that we will use, and the other one we will determine how we will use the voltage reference. So here's the register for the determining the voltage reference. As you see here on the 8MeGa32, we have 3 bins, 32, 31, and 30. The 32 is for the analog reference, and 31 ground, and 30 for analog VCC. So if you will use an external analog reference, so you will put these 2 bits, the ref S0 and ref S1 by A00, and you will connect here the analog reference. And if you will use the analog VCC, so you will put like an external capacitor, as we saw on a previous example on the video. We will put an external capacitor to the ARF bin, and you will use the AVCC. And also, if you use the internal voltage with 2.56 voltage, you will put an external capacitor on the ARF. I think this was the example. So based on the voltage reference selection that you will choose, you put the values for these 2 bits, ref S0 and ref S1. For choosing the channel, we have here like 5 bits here, from max 0 to max 4. So if you decided that you will use the ADC 0, so you will write here on this bits, you will write 5 zeros. If you will use ADC 1, you will write 4 zeros 1, and if you will use ADC 7, you will write 0 0 1 1 1. Also, we can recall that our ADC channels is only on port A, as you see here. So this port A have a dual function. It can works as a digital port, and also it can works as an analog input channel. Then we have another register, which is the ADC control and the status register, ADC SRA, because this is the name that you use on the code. This register is responsible for several things. Enable the ADC because on all microcontrollers, they make the option of enabling and disabling the ADC block, so it will not consume power when it's not operating. So when you want to operate the ADC, you have to enable the ADC, and if you don't need it, you will leave it disabled and to not consume a power from the power of the microcontroller. Also, we will determine in this register, the ADC control and status register, the frequency of the ADC, how the conversion process started, how it will finish, and also if we use entrance. To determine the division factor or the prescale, we will use these 3 bits. It's called ADBS2, ADBS1, and ADBS0. So if you want to make a prescale or a division factor of 64, so you have to put a 1 on ADBS1 and a 1 on ADBS2. This is 0, so it's not needed to make it. So if we will write a code, so we will write ADC SRA ordered ordered with one shift ADBS2 and one shift ADBS1. For enabling the ADC, we have this bit 7. This bit 7 ADEN means ADC enable. So if you put here a 1, it means that you enabled the ADC. If it's a 0, so the ADC will be disabled and you can use port A as a digital port. Also, we have this bit ADSC. It means ADC start conversion. So if you put here a 1, the conversion process will begin. And when the process of the conversion ends, so it returns back to a 0. Also, we have another bit, which is the ADAT. ADAT means ADC auto trigger enable. This means that when we put this bit a 1, the ADC is triggered automatically. And if each on each edge of the clock pulse, the ADC works automatically. And we will need the register of the SFIOR register for this sake, and we will elaborate it in details on a while. The ADC interrupt flag, which is ADIF, this bit a flag that tell us if the conversion finished or not. So if this bit becomes a 1, that means the conversion is completed and the digital form is ready on the result register. But if it's still a 0, we have to check it another time until its value goes to a 1, and we will know that the conversion is completed. We have ADIE, which is called ADC interrupt enable. So if we want to enable the ADC interrupt, we have to put this bit by a 1. And if we don't, if we will not use the interrupt, so we will leave it like a 0. The register of the result, it's called ADC data register. We have two register. Why we have two register? Because the ADC on the 8MEGA32 is 10-bit ADC, 10-bit ADC, and our 8MEGA32 is an 8-bit microcontroller, which means that the size of the registers on the memory is an 8-bit registers. So the 10-bit will not fit on a 1 register. For this reason, the result is divided into two registers. From ADC 0 to ADC 7, it will be on a register ADCL. L means low, and this is the lower bits of the result or the digital form of the analog signal we converted. And ADC H means high, which is the high bit or the most significant bits. We have only remaining 2 bits, which is ADC 8 and ADC 9. And take care that this register is read-only, and you read from it the digital value of our analog signal converted by the ADC. Then we have this register. It's called a special function IO register. This register is operating only on the status of using the auto triggering for the ADC. And this register is like a flag for the ADC. If we here this bits determine the trigger that makes the ADC to operate. So we having here different types of triggers. It may be an analog comparator that you have two values, and according to the output of the comparator, the ADC will begin operating. So, for example, if the output of the comparator is 1, the ADC will work, and if it's 0, it will not work. Also, can be an interrupt. It can be a timer. Maybe you set a timer. So if the timer finish and the timer goes to a specific value and then reset, so the ADC will begin working. So this is different types of triggers. Now we will make a lab task for the ADC. In this task, it's required to use the ADC on the 8MEGA32, and you can change the analog value from a potentiometer outside it, and we will display the digital value on a LED on the PCB. So the value of the high voltage, it from the range of 2.6 to 5 volt, and the lower from 0.5 to 2 volt. Let's see the code. So as our famous beginning, we have to make some definitions. So firstly, we will define the operating frequency of the ADC, which is here 16 megahertz, and then we include the header file of the AVR IO, so we can use the ports. Here we will use the interrupts of for the ADC and also the delay function. And we here define a variable x. We will use it to determine which channel we are working. So here on the first step, we will determine the voltage reference selection that we will use. So here we choose the AVC as the reference, and we will have the 5 volt as a reference. If we recall this from the register, so you will recall how we get these values. So here we choose this option that we will use the AVCC with external capacitor at a ref bin. So we need to put a 1 on the ref S node. Go back to the code. Then here, the AD max, we will select the analog channel that we will choose. We will put it an X, as X is the argument that our function, which is called initiate ADC, will take. Then here we will choose the pre-scaling. We choose pre-scaling 1 to 8 frequency. This is the range from 50 kilohertz to 200 kilohertz. And this also needs to put 111 to all the ADBS bits, ADBS0 and ADBS1 and ADBS2. And then we enabled the ADC by put a 1 on the bit of ADEN on the register of ADC SRA, which is the control register. And here we enabled the interrupts. The SEI is the global interrupt function, so we put it, and then on the end of the function of the initiate ADC, we will put a 1 on the ADC AD start conversion bit, so the ADC will start conversion after initializing the ADC by this parameters. Then here we will make interrupt function. This interrupt function took the ADC vector, and then it will, if the value of the voltage ranges from 0 to 5 volts, so the port C will be the bit 0 on port C will be a 1, and else if the range from 0.5 volts, this ADC bit 4, it will be a 1, and if greater than the range of 2.6, it will be bit 7, it will be a 1, and so on. And here we will make the ADC start conversion again, but putting a 1 on the ADSC. So this is the main function that we want according to make like an interrupt according to the value of the input voltage that comes to the ADC. We categorize the range of this input voltage, and according to the value of it, which will be represented by the digital equivalent of the signal, the port C will turn on a LED. As you see here, the ranges. Finally, the int main function on the beginning to make the interrupt action, which is turning on some of the LEDs connected to some of the bits of port C. We will make all port C as an output. So we will put on the DDRC. DDR means data direction register of port C. We will put all the DDRC with a 1, which means that all of them is an output. And then we will initialize port C, and then port A is the input channel, which is having the analog input channels. We will make all of it as an input, and then we will call the ADC, and we connected our analog input to analog channel 3 on port A, and then after calling it, we will make like a while one, and then we initialized the port C, and when the ADC channel ends, so we will make a while one for port C to be a 0, and then and so on and so on and so on. This is the code, and that's it for the ADC. If you have any question, please don't hesitate to send me an email. Thank you.